Welcome to the first class of Advanced Microstructural Characterization by Atom Probe Tomography and Electron Microscopy. My name is Surendra Kumar Makineni. I am a faculty assistant professor in the Department of Materials Engineering at Indian Institute of Science, Bangalore. Okay, so before going to the topic, I just want to show you some of the reference texts which are very important for this course. The first part of the lectures will be on atom probe tomography, and the second part of the lectures will be the transmission electron microscopy. So these are the three books which are very important and will be very useful throughout the course lectures. So the first one is by David J. Larson and his colleagues, where the book name is Local Electrode Atom Probe Tomography. There is another book which is a very useful book related to the concepts about the field evaporation and field ionization, and it is written by Baptiste Gault, and this is Atom Probe Microscopy. And the third book is Atom Probe Tomography, the Local Electrode Atom Probe, where it is more on construction of LEAP, which is an advanced version of the Atom Probe Tomography, and some related to the basics. In transmission electron microscopy, we have a very old book which is called Eddington, written by Eddington, and it is a practical electron microscopy and material science. And there is a very another book is Transmission Electron Microscopy by Professor Williamson Carter, and also there is another book which is Electron Microscopy and Analysis, which is for the reference texts. Okay, so as we know that we are surrounded by several materials, and without which our daily life is always depends upon them. So for example, in the construction and skyscrapers, we use a large amount of steels and also high strength steels so that they can sustain the loads for a longer time. Okay, and in automobiles and lightweight alloys, so usually we use magnesium and aluminum based alloys, and these are typically for the powertrain applications, and also the engine parts, especially the piston and the chamber, correct. So and the main thing is to lower the weight, and also to get the without any compromise on the strength, correct. So to sustain the loads during operation of the vehicles or automobiles. The third class of alloys, which are very important for the defense applications and for also the aerospace industries, these are called super alloys. Okay, so these especially are very important for high temperature applications, where a typical jet engine, where the turbine engine, the material they have to sustain a temperatures about 1500 degrees Celsius. So we use a special class of materials which are called super alloys. In the rocket engines also we use large amount of super alloys, and also the another class are the copper alloys, which are used for the conductive applications, because to increase the heat transfer, correct. And these copper alloys should also sustain loads at very high at room temperature and at moderate like up to 300 to 400 degrees Celsius. So these all alloys, these materials, they have a specific features, microstructural features, fine. And as my course as the course title says, the advanced microstructural characterization, correct. So these are the microstructural features, microstructural characterization by atom probe tomography and electron microscopy, fine. So we will go one by one, fine. So these microstructural features, what are these microstructural features? These are grains, grain boundaries, phases, precipitates, defects. These all consists in the microstructure, which all controls the properties. Properties can be anything. It's like functional properties, mechanical properties, and magnetic properties, but all these properties can be controlled by these microstructural features, or by tuning the volume fraction of these features, fine. And these features can be directly fine tuned by using by studying the phase diagrams and solidification and phase transformation, correct. These are the three important things which are very important to design the microstructure. Okay, so in designing the microstructure we need the phase diagrams, we solidification and also the phase transformation. We will not go to the metallurgical aspects of these microstructural features. Our main concern is to how to characterize these microstructural features, because these features ultimately controls the properties, fine. And especially my area of interest is physical metallurgy and also the mechanical properties, correct. So mostly it will be covered on the mechanical response of these alloys. Now characterization can be done, as I told you, by atom probe tomography. What is atom probe tomography? It gives the chemistry, fine. Chemistry means what is the chemical composition of these microstructural features, fine. Electron microscopy, it gives the structure, fine. So this structure, so it's like atomic structure, fine. And these structure and chemistry, these are actually coupled, these are always coupled, fine. And due to this coupling effect, ultimately these two aspects ultimately controls the property of that material, fine. And the chemistry and the structure, both these are different for different microstructural features. Okay, so for example, if you talk about grain boundaries, these we call as a grain boundary segregation. Okay, and for phases it can be a composition, correct. For precipitate, these can be a precipitate composition, and it has a certain structure which can be different from the matrix phase. Okay, so here I am showing you some photographs where it is just photograph of an atom probe which is located in ISC in AFMM, and also the microscopy where both of them are located in the AFM center in ISC. So bottom left image, where you can see this sequence of spheres, correct. And these aligned spheres are nothing but these are atoms which are aligned periodically, fine. And these are actually 100 planes. Okay, so at each plane you can actually visualize these atoms, or you can get the chemistry at each plane, fine. And here at the right side you can see the atomic column. These are atomic columns, fine. And this particular region which I am enclosing is one kind of precipitate. Okay, and you can see these precipitate, if you see these lattice planes, these are actually continuous, fine. And this means these continuous planes, it is directly related to your what we call as a coherent precipitates. And these precipitates are very important because these precipitates actually strengthens the matrix, and the interface between the matrix, we call it as this is a matrix, this is a precipitate, and the interface of the matrix and precipitate plays a very important role on the stability and the strengthening of the alloy. Okay, so as I told you, I have just briefly explained the microstructural features, and here it is a very nice diagram where it shows this is the surface, fine. This is the surface at the right side, and you can see at the surface this is a cross section of the of a typical microstructure which we see underneath, fine. So this is the surface, and if you see that we'll have a grain boundaries, we'll have a grains, fine. These are the grains, and we have a precipitates which is it might be inside the grains and it might be at the grain boundaries. We have in the microstructure can also contains voids at the grain boundaries and at the interior of the grains. These grain boundaries are enclosing a particular region. Okay, so this I am marking at the center, and this one particular enclosed region is called grain. okay, and this grain is nothing but a one particular oriented in a one particular orientation, crystallographic direction, or we may tell it as a single crystal. And these single crystals, if they are arranged in a random fashion, correct, you can see that these are randomly arranged. These can be, which are sharing the grain boundaries, which shares the grain boundaries. So it means that if you go from this particular first grain to the second grain, your orientation will change once you reach the second grain, and these are called grain boundaries which are enclosing these grains, correct. So this is typically a grain structure which we see in a typical microstructure. If you go little bit more details at higher magnification inside these grains, you can see that there might be a twins, there might be stacking faults, there might be dislocations, correct, in the inside the grains, and ultimately these are the features which directly controls the overall property of any material. If you go still in higher magnification at the atomic level, we can see that there might be the vacancies, there might be the atoms which are substitution atoms, there might be some interstitial atoms which can strain the lattice, okay, inside the grain. Due to that strain, it will directly impact the property of the material, especially the mechanical property, okay. So this is the arrow mark which shows the scale where microstructural features at different length scales, correct, and these microstructural features directly controls, as I told you, electrical, optical, mechanical properties. They also directly control the corrosion resistance, radiation resistance, hydrogen resistance, which are very important for the hydrogen embrittlement effects in the microstructure. So now what I will go through is briefly explain you the how a microstructure develops in a particular material. Fine. So if you consider these are the atoms which are arranged in a disordered. For example, if you can consider these as a liquid, and every element, if you consider one element, every element has a certain melting point, correct. So above the melting point it will have a liquid in a liquid state, and below the melting point it will have a solid state. Fine. So if you go below the melting point, these atoms will arrange in a certain crystallographic fashion, okay. So they what they will do is, first they will form a nucleus. So the formation of this nucleus, it's a fluctuation process, correct. So it is like, for example, some of the atoms will come together, they will go and they will detach themselves, but at a certain point they will reach a critical size, R critical, where the atoms comes together and they reach the R critical size where the crystal is stable. Fine. And this we call it as a nucleus. Fine. And this nucleus, what will happen, the more and more number of atoms will attach to that particular nucleus, which is having a certain crystal structure. Fine. And that is how this grows in a microstructure. So we call this as a ordered arrangement of atoms. Fine. Now if there is a liquid, okay, if there is a liquid, now it might possible that the nucleus can these atoms can comes together to form a nuclei at different locations. So first location, second location, third location, fourth location, fifth location. So they can nucleate at randomly at any place in the liquid, correct. So what it will, as I told you, these nucleus will convert to a certain crystal structure, okay, which is having a crystal structure at some periodic arrangement of atoms. So at each location it develops a periodic arrangement of atoms of the crystal. So this is crystal 4, this is crystal 3, this is crystal 2, and once this solidification is completed, what we get, it is a grain structure. So here for the one, so this particular grain corresponds to one orientation. This is the second orientation, third orientation, fourth orientation. So this is how overall a microstructure develops, which is these grains are surrounded by these grain boundaries, and these grain boundaries have a misorientation. Mostly it is more than 12 to 15%. These are called grain boundaries. Fine. So it means that the crystal structure at the grain 1, the orientation of the crystal structure at the grain 1 is different from the grain 2. Correct. Now for it means that if there are atomic planes which are in this direction, in the grain 5, at the grain 4 these same atomic planes will have a different orientation. Correct. So this how develops the overall microstructure of the alloy. So here I am showing you an electron backscatter diffraction pattern, where you can see that will not go into the details of this, but on the one thing to remember is the color, the orientation is directly related to the color is directly related to the orientation of the crystal. It means that this particular big grain, the purple grain, is having a one particular orientation crystal structure, and having a one orientation of the crystal. Fine. And this red color will have a different orientation, this green color will have a different orientation, but overall the crystal structure of the complete microstructure is same, only the orientation of the crystals are different, and these are surrounded by the different grain boundaries. So if you go to the if you go to a particular grain, what we described here as a crystal here, so the atoms are arranged in a periodic fashion. Fine. So this is a particular unit cell, correct, and it has a certain lattice positions, and each lattice position is occupied by one atom. Fine. It is occupied by one atom, and if these atoms are arranged in 3 dimension, in all the 3 directions, x, y and z, then you will develop a complete crystal or the grain for that particular microstructure. So it is just a repetition of the unit cell with the atoms sitting at the lattice positions. Okay. So this is just a basic thing which how the microstructure develops, and in the coming slides you will understand that why this is important to understand the characterization techniques. Fine. So another important part. So as I told you that as we discussed about the crystal structure, correct. So and as I told you that these are arranged in a periodic fashion. Fine. These are arranged in a periodic fashion. The atoms are arranged in the periodic fashion. Now between the atoms in a solid there exists an interaction. Actually they can so these atoms are held together to form a crystal which is together. Okay. So there is an interaction between these two atoms. For example, first atom and the second atom, there is a certain interaction. Fine. And this interaction is divided into two important concepts. Okay. So one is attraction and another is repulsion. Okay. So these are the two important aspects of the interaction between the two atoms. So first we discuss about the repulsive force. Okay. So when an atom comes close together, okay, so what will happen, the electron cloud of the atom will starts overlapping. So these electrons are negative charge. So what will happen, these negative charge will develop an repulsive force. Fine. And this repulsive force, okay, is termed as 1 by r to the power of 12. Okay. And this equation is a famous equation which is by Sir John Leonard Jones. He was a British mathematician in 1924. He has developed found this equation where it explains the interaction between the two solids or the two atoms. Fine. So as I told you, the repulsive forces is directly related by the 1 upon r. R is the distance between the two atoms. Okay, so and it is directly related to the 1 upon r to the power of 12, which is related to the repulsive action. Okay, similarly there is an attraction. Okay, so as your distance increases between the atoms, so it has a certain mass, correct? Atom has a certain mass, and if two masses are present together, always there will be a attraction between the two masses, correct? So there will be when the two solids go away from each other, it develops an attractive force between this. Okay, and that attractive force is related to 1 by r to the power of 6. Okay, so there is a first variable which is called repulsive, which is 1 by r to the power 12. That is, second is the 1 by r to the power 6. Fine. So these are the two forces which are very important for to generate to understand the interaction between the two atoms. So the attractive forces are directly related to, or what we also call is a van der Waals forces. Van der Waals forces, and these are very weak forces. Fine, these are very weak forces. Okay, so at a very large distances, this particular equation is plotted in this. So this is your potential energy U. This is the distance between the two atoms. Fine. Now this dotted line corresponds to the repulsive term. The down dotted line, the dashed line, it corresponds to the attractive term, attractive energy, and the resultant potential energy curve is this dark continuous line, which is the resultant of the repulsive and the attractive force between the two atoms. Okay, as I told you, these repulsion forces are directly related to the 1 upon r to the power 12, and attractive forces are related to the 1 upon r to the power 6. In this equation there are two other terms, which is called sigma, which is called eta. Fine. And what is sigma and eta? So if you see this resultant potential energy curve, you can see that there is a minimum point. There is a minimum point where the potential energy is minimum, means it is the most stable state at that particular distance of r0. Fine. So if the two atoms are coming close together, then initially there will be an attractive force. Once it comes closer and closer, there will be a position, there will be a state where the potential energy is minimum, and this minimum distance which is maintained, where the state is having a lowest potential or the stable state, this corresponds to r0. Okay, and this also termed as a equilibrium distance. So as I told you, in this equation we have two terms, eta and sigma, and epsilon, we can call it as epsilon, eta or epsilon, eta and epsilon, and it is epsilon represents the depth of this potential energy curve. Okay, so it represents the depth, or we can tell it as it represents the potential well. It represents the potential well of that particular potential energy curve between the particles. Correct. And sigma, what is sigma here? Sigma, it represents the distance at which your potential energy, your U, is equals to 0. Correct. So this particular distance is related to sigma. Fine. Where the actual potential energy is 0. Fine. So now you understood this equation, where this is the resultant potential energy curve, or it shows that the distance which is maintained between the two atoms at a very lowest potential energy state. Fine. And this dip corresponds to your epsilon, and the distance at which your potential energy U is equals to 0 corresponds to sigma. Okay, and this model actually provides a useful way to balance, to understand the balance between the attractive and repulsive forces that governs the behavior of atoms and molecules at various physical and chemical systems. Okay, so we have briefly discussed about the microstructure formation. We discussed about the grains, we discussed about the atoms which are sitting in the unit cell, and these unit cells are repetitive and they form a complete crystal state, or the grain, and these grains are oriented in different orientations, correct. These then they will have a grain boundaries in between the grains. Now this course is related to the atom probe tomography to get the chemical information at the atomic scale. So we briefly discussed about the atomic states related to the potential energy curve. Okay, so about the Lennard Jones potential. Fine. So now before going to the main basics related to the field evaporation and field ionization, which is a crux, which is the critical for to understand the atom probe tomography, we'll just briefly go to the history of evolution of this technique, correct. So as we know, Professor J.J. Thomson in 1897 he has discovered electrons, correct, and it has a certain charge and also the mass, correct. And later Professor Rutherford and his colleague Bohr, so both of them, they actually found the structure of atom, correct. And the structure of atom, it means the electrons are at the certain orbitals which is having a certain energies, fine, and the nucleus contains protons and neutrons, fine, and protons, they have a equal charge to the electrons and but a different mass than the electrons. So electrons are much lighter, but the neutrons, these are, as the term, these are neutral atoms, they don't have any charge, but the mass is similar to the protons, correct. And here I am showing you atomic structure of a carbon atom where the atomic number is 6 and the mass is 12. The mass atomic mass 12 means there are 6 protons and 6 neutrons, which comes out to be a 12, fine. So this is the structure of atom which was proposed in during the 1911 and 1913. Later Professor Bragg described is the atomic packing of these atoms in a certain crystallographic pattern, correct, in a certain crystal structures. So they provided the experimental confirmation of the atomic packing of atoms in crystals, correct. So how these atoms are arranged in a periodic fashion. So in 1928 there was a big development happened where Professor Fowler and Northam, both of them, they have showed that the by providing the electric field, we can actually strip out the electron from the atom, correct. And this field electric field requires a huge amount of voltage application, so it is around 10 raised to the power 9 volt per meter has to be applied, and such that the magnitude of, because of the magnitude of the electric field generated, we can actually strip out the electron from an atom, fine. So this was the first time which they predicted the magnitude. So here I am showing you a sphere, okay, and of radius r, and if you apply a voltage, a very high voltage, so based on the radius, so this radius r, it is directly related to the radius of curvature, and this particular r, so then the field, the electric field F is directly is equals to V by R. So smaller is, larger is the radius of, smaller is the radius of, or smaller is the radius, or higher is the curvature, then more will be the electric field generated around the sphere of around the sphere, correct. And at a certain voltage, for example, as I told you, they have predicted around 10 raised to the power 9 voltage per meter. If there is a if voltage, then it we can strip out the electron from the atom. After this work, in mid 1930s, Professor Gustav Hertz, he has taken one PhD student whose name was Erwin W. Muller, and the main task was to design field electron emission microscope. Okay, so as the name suggests, it is to generate a very high electric field such that the electron can be emitted and accelerated, which can be used for imaging purpose. Okay, and in 1936 Erwin W. Muller was the first person who has designed this FEE microscope, and what he did is he has taken a element tungsten element and he has sharpened that tungsten into a very sharp needle which is around approximately 100 nanometers. And this is the setup, this is the schematic of the setup what he has used it. So this is a tungsten tip. Okay, this is a very sharp tip around 100 nanometers. This is the phosphor screen. Okay, and at a vacuum, it was done under high vacuum, and a very large potential of negative potential was applied on the tungsten tip, due to which at the phosphor screen he has recorded an image where you can see that there are 4 bright spots, diffused spots, correct, and this tungsten needle was oriented in 110 crystallographic orientation, and due to this orientation the tungsten has a BCC crystal structure, and along the 110 direction it always shows a two-fold symmetry. And exactly in this image where you see these bright diffused spots or the contrast, we can see that these are also a two-fold symmetry. Fine, actually, so it means that these are the electrons which are recorded on the phosphor screen, which are accelerated on the phosphor screen, correct. With this microscope he has achieved not more than 2 nanometer resolution. Okay, and he was the first person to design this FEM microscope. With this we will end the first class, and in the subsequent class we will talk about how by reversing this potential, how a new field FIM, field ionization microscopy, has been developed by Muller.